on this to do the product rule. I mean, you can do the product rule, but it's not necessary to do the product rule because ln of 2 is just a constant. And if you think about the derivative of ln is u prime over u, if you pick u as 2, then the derivative of u would be 0. So if it's just a number, ln of a number, you could do that on your calculator and it's just a decimal. And so you can treat it as just like the constant multiple rule, where you can just leave this alone, take the derivative of this, right? Just like if it was like 2 log 2, you would just leave the 2 alone. You can do the same thing with ln of 2. So you can just leave ln of 2, and then the derivative of log 2 of x would be the derivative of x is just 1. So then that would be 1 over ln of 2x. Is that true? And then these just cancel.
Yep.
So it's just 1 over x.
If x is greater than 0.
Yeah, where is it? Yeah.
Because, like, really it's implied in the top. I don't really know why they have to say it here. I don't know if it says in the directions to say that. But I think it's implied in this. When you do this problem, could x be negative up here? Could x be 0 up here? You can't take the log of 0 or the log of a negative number. So they're telling you this is only true when x is bigger than 0 because the equation's not defined when you take the log of 0 or the log of a negative number. Not really that big of a deal. I'm not going to ever mark it wrong if you don't include that. But if they asked you to find the derivative at negative 2, it's important that you don't tell me the derivative is negative 1/2, because although it seems like it's negative 1/2, you couldn't do it because the actual function isn't defined for that. So they're just kind of reminding you that the domain is restricted. But I think that was a good reminder that ln of 2 is a constant. 29 and 31.
I got as far as solving x.
Look how it's written as well. I'm going to look here.
It's
29 says, at what point on the graph of y equals 3 to the x plus 1 is the tangent line parallel to the line y equals 5x minus 1. So if I want to know where is this line, tangent line of this graph parallel to this line, that's telling me I want where their slopes are the same, right? Because that's what parallel means. So easy part of this is I can tell the slope of this line is 5. So that means another way of saying this problem is I want to know when is the slope of this tangent line equal to 5. And we know that means the derivative. So it's saying when is the derivative of this equal to 5. So you got to find the derivative, set it equal to 5, which means you do have to do a little bit of equation solving on this. So I just found the derivative, and the derivative of 3 to the x is 3 to the x ln of 3. Is that true? And then I just set it equal to 5. Well, not going to eat it because the point is we want to get this x by itself. So I divided by ln of 3 first. And then the only way to get that x out of that is to ln both sides again. And so I have ln of 5 over ln of 3 equals ln 3 to the x. And again, the reason that I do that is so I can bring that x out front using that property. So I would get ln of 5 over ln of 3. I'm going to go ahead and divide by ln of 3 again. Move that over. That's what I got as my x value. And again, I tend to wait till the end to type that in my calculator so I don't get any error there. It asks for the point. So this is just the x value. So I did type that in my calculator. And when I typed it in my calculator, I got about 1.379 as the x value of where the tangent line would be parallel to this graph. And so to find the y value, I just plugged that in. I just said 3 to the 1.379 plus 1, and it ended up being 5.551. So the point where this graph's tangent line is parallel to this equation, which means where they have the same slope, would be approximately that point. So let's look at 31. 31 says a line with slope m passes through the origin and is tangent to y equals ln of 2x. What is the value of m? And maybe there's probably an easier way to do this than I did it. But it said a line with slope m that passes through the origin. So that would be a y-intercept of 0 with a slope of m. So I said that would be the line y equals mx. Do you agree with that statement? You just see all these arrows drawn on my paper. It really makes no sense. So it says, what does it say? Passes or is tangent to this line over here. So tangent, I was like, I need a derivative at some point, so I went ahead and did the derivative. Because, you know, when all else fails in a calculus problem, you just take the derivative, right? And u prime over u would be 2 over 2x, or that would just be 1 over x. So if it's tangent and this is the derivative, do you agree that I could plug 1 over x in for m? Is that statement or no for that statement? All right. So here, let's humor me for a minute on a couple things. If I have this, y equals ln of 2x, and if I have y equals mx, thinking about trying to solve for x, let's go back for a minute and quit thinking about derivatives. Thinking about back in the day when we did substitution elimination, if these both are equal to y, could I replace this y with ln of 2x in terms of getting those both in terms of x? So I did that, and then I said, okay, I still can't solve it because I have an m and an x in the problem. M is slope. If it is tangent to the graph, that means the slope has to be what the derivative is. So then I plugged in 1 over x here. And then I just solved that equation for x because that cancels out. And I'm left with ln of 2x equals 1. So I e'd both sides because that cancels out the ln. And I got 2x equals e, or x equals e over 2. Now here's the tricky thing about this. This is not the answer. Look at the back of the book, it's not the answer. And again, maybe I did this harder than I should have. Passed over is tangent to this. What is the value of m? M is slope, right? I found the value of x. If I want to find the value of m, I want the value of the slope. So I took this and I plugged it in here to get 1 over e over 2, which is 2 over e. That's kind of a crazy problem. Are you ever going to have a problem like that on a test? I know it's kind
I
of
feel like we found like 3 different slopes though.
Why did you plug that into the derivative? Oh, because you needed another slope?
because I needed to find the slope, like at that. A line with slope n passes through the origin and is tangent to this graph. So normally when we do a problem, they say, find the equation of the tangent line given a point, right? We do that all the time. This is kind of like going backwards. They gave you the equation, and they said, it goes through the origin, but I'm not going to tell you what the slope is, so you had to use the derivative, right? Like, this is the derivative at any point on this graph. Do you agree? Like, I could say this is the derivative, and then I could plug in any value in the domain, and I could find the slope of this curve using this.
So then you have to figure out what they intersect.
So you had to figure out where they intersect, which is why I said them equal to each other. Plugged in the slope, meaning like the representation for slope, which is 1 over x. But I still needed to find like that point where that line would cross ln of 2x to be tangent to it. So I found the x value. It didn't ask me the point that they cross. It asked me what is the actual slope. So then I took that value and plugged it into the derivative. Like I said, kind of a terrible problem, but it takes me a while to kind of go through my work.
I was not confused finding out 7.
7?
Yeah. Here on top.
E squared, here's the big thing for this one. E squared is just a number. Do you agree with me on that? Like E squared is not a function. Well, I mean, like it doesn't, you don't have to do the product rule on here because the derivative of E squared is not E squared, it's 0. Does that make sense of what I'm saying? Just like the derivative of pi is 0 because it's actually a number. So E squared, if you did the product rule here, the derivative is 0. So I didn't do the product rule. I just left it like a constant and said the derivative of x is 1, and then I left the E squared minus the derivative of e to the x is e to the x. So you have to really think about, there's no x in this, so it's not something that you need to think about using the derivative rule.
That was out front of the x.
Yeah, like I would probably write it as like this, e squared x, if you think about it as like a constant in front. What was one other one, what was that one, Jake, that we talked about with the crazy rule? 21, was that the one with the crazy ln rule that I, I think it was 21. Last one, I'm doing this one, then you can see me for more. It gave 2 answers in the back for this, but I just want to remind you, this is what I said about the crazy ln rules that they do, and sometimes you think, what in the world? But if you do the derivative of this, you would say u prime is 2x over x squared ln of 4. Sorry, I always have to think about that derivative. And so you can definitely cross one of these x's out, and you get 2 over x ln of 4. When you look in the back of the book, they say the answer is 1 over x ln of 2. And in Calc Lab yesterday, Jake said, I thought you said you couldn't do this. You can't cross out the 2 and the 4. And it's true, you can't cross out something up here with something down here. But they always tend to simplify powers of 2. So how do they go from here to here? They said, well, ln of 4, could I really think of that as ln of 2 squared? And then they pull the 2 out front. So then you get 2 over 2x ln of 2, and then the 2's cancel out. I was telling Jake yesterday, I would never mark you wrong on a test if it was just an open-ended question and you left your answer like this, and the answer book said this, because it's kind of like a jump to get there. But it's something that shows up a lot in this book, and so it's why I want you to check your odd answers, because a lot of times, the first year I ever did problems out of this book, I never would have automatically thought that, but now when I see powers of 2, I think that because this book has trained me to say, oh, I wonder if I could pull a 2 out. But it's one of those that I look in the back of the book sometimes and I'm like, oh, darn you, ln of 2, ln of 4. So I just wanted to let you know that you cannot cross these out. It just happened to work out that way. Like if that was a 4 on the top, and that was ln of 4, you would still only be able to pull a 2 out, and so that would change things. It wouldn't just be like 1 over 1. So I just want to make sure I addressed that. Okay, and I'll answer more questions individually if you have them, but I really want to get started on today's notes because they're super exciting. They're not printed because they're not, the problems are long, so you want to have your own paper. That's why they're not printed. Like there's not much writing. It's just working things out. This is our last day of chapter 3, kids. Our last day of new notes for chapter 3. And the only other chapter we're doing this whole semester is chapter 4. So it's pretty exciting. And chapter 4 is just applications of derivatives. No new derivative rules. Just applying those derivatives. Kind of to real life. Kind of a lot about graphs. Like we're going to be able to use what we know about derivatives to talk about a lot of things about graphs, but we will talk about velocity acceleration stuff.
That's really sad.
we will maybe sketch a few graphs using derivatives. So we're going to learn how to differentiate something like x to the x. Think about that right now. We don't have a rule that we could do x to the x. You're not allowed to just pull the x out front and subtract 1, right? You can only do that if that's a number. That's not an e to the x or an a to the x, and so that does not fit any of the rules I've given you. So we're going to use what we know about logarithms and ln to figure out how we can take the derivative of that. So that's pretty exciting. And it's a lot of fun. And when I say that, that probably means you're going to think it's not a lot of fun. So that's my sarcasm.
Like problem one.
I don't know the answer to that. All right, so here is your rule. And again, the book writes it like this with du over dx. I changed it to u prime if you prefer it like that. But if u is a positive differentiable function of x and n is a real number, then we can take the derivative using the power rule that we've really always thought of. N is any real number, not an x. Then we can take the derivative, and I feel like probably you could figure that out, but it just gives you some weird ones today. I use less paper. I use about the same paper for tonight's homework that I did for last night's homework. So, like, less problems tonight, but they do take longer, but there's less problems, so it should be about the same, I would think. And so, I wrote it out like this, and again, we talked about it once before that they changed from an integer power to a rational power, and now they're saying n can be any real number, which means we don't see this very often, but they could give you a problem and say find the derivative of x to the 1 plus the square root of 2. You can still do the power rule. You just have to make sure you subtract correctly, and you just bring it down front. And so it looks a little uglier, but the same idea is still there. So hopefully that part of the homework won't be so bad to do. Philip, your shirt is so bright, I don't even know how to handle it. Did you see Mr. McClure out there this morning?
Yeah, what was he doing?
Returning the school laptop that he still had in his house. He texted me Saturday night and said, "Hey, I just ran across my school laptop. You think I should bring that back?" And I said, "Maybe." So,
I still have my yearbook from Great Pass last year, so it's Chloe. And they never said anything about it, so I just kind of left it at
I
home.
still remember when the photos of the shop picture that he said he left for a higher quality.
Mr. Puckett wrote that on
For
he left us for a higher power. So people that didn't know, it almost thought he died on the paper. I made us laugh. Because Mr. Puckett always goes through and tells you where everyone went.
It's kind of funny because it almost sounds like your math.
A higher power.
so dydx means
The derivative. It's the same as y prime.
It just always confuses, like, whenever we take the derivative of y, like, if it's like 2y, then we have to write dy dx. So it's like, I don't know.
So it's like, that's where this comes from, because if I took the derivative of this y right now, it would be 1, right?
Yeah.
But then I'd have to put dy dx. So if you want to think about it as implicit, you can. I just like to use it sometimes just to remind you that it's also the same as the derivative. It's the same as y prime. It's the same as f prime of x. No, d over dx means take the derivative of this, and this is what you get. D over dx means do the derivative. dy over dx means this is the derivative. Does that make sense?
Yeah.
And so if I take the derivative of this, I'm just going to do the power rule. So I'm just going to bring this down, and I'm just going to subtract 1 from this. And if I subtract 1 from this, do you agree that's just going to cancel out that positive 1? And it's just going to leave me as x to the square root of 2. That's it. Right. This is a constant, and so it's just. Oh, u prime. This is u. So the derivative of x is 1. Sorry. Say that again. Yeah.
I thought we were doing a new rule.
Well, this is the new rule / power rule, right? Like you bring.
Okay, so power rule, but it's going to be stating like if it was a variable up top, it would still be the same.
No, not a variable, n is just a real number. It's really nothing new except for the if part tells you that n can be a real number. That's all it's saying, because we haven't done irrational powers yet. We've only had rational powers.
Oh.
Does that make sense? And so it's really the same rule, they're just saying, hey, now the exponent can be irrational.
Okay.
That's silly, right? They should just tell you all at once. But they like to make it nice and pretty for a while. Only integers, and then we could throw in fractions, and then we throw in irrational. This is not the new rule. This is just throwing in, what if I throw in an ln into a big chain rule problem, and you just have to make sure you take all the derivatives, like inside the function, and you don't forget anything. Also remember, when you do the derivative of ln, if you're thinking of the derivative as u prime over u, then you're taking care of the derivative of that super inside function right now. So let's see here if this makes sense. So starting with the outside function, that's going to be starting with this 2, right? I'm going to do the power rule. So I'm going to bring the 2 out front, and I'm going to leave the inside alone. ln of 2x plus 2 to the first power. And again, when it's a complex function, like a lot of things in it, sometimes it helps to like cross out. I did the outside function. Now I'm going to do the inside function. So now I'm going to take the derivative of ln of 2x plus 2. And although it's kind of a chain rule problem, if you're doing the derivative as u prime over u, you're already taking the derivative of u prime. So don't double chain rule that problem, which is what happens. Also, a lot of people have been adding with the chain rule, but we always multiply. So remember, you multiply times the derivative of this, which would be the derivative of u prime would be 2 over u, which is 2x plus 2. That takes care of the ln and the u because we did u prime over u. Definitely we want to simplify stuff. So I definitely can not cross anything out because I can't cross this out with this. Do you agree with that statement? Because that is stuck with that ln. But I can take 2 times 2, which is 4, and I'm just going to write this as ln of 2x plus 2.
Well, even in that like fraction right there, could you
Ooh,
take 2 out
I could
from
take a
the
2 out of the bottom. You're genius. Right?
But don't you have to prove the
We did already though, right? By doing the 2 on the top. You see what I'm saying? Like when we do u prime, yes. That's all of the derivatives in 3.8 and 3.9. All the inverse trig derivatives and all the ones I gave you yesterday, they gave you the derivatives in terms of u so that you didn't have to think about, oh, do I need to multiply by the derivative of the inside because they're already doing u prime. Again, this is one where if it's odd, I would say check the answer or just be aware they could write this a few ways. I would leave my answer like this, 2 ln of 2x plus 2 over x plus 1. But could I, right, could I put the 2 up there and make that ln of 2x plus 2 squared if I wanted to? Would that also be an acceptable answer? Would you ever have to do that? No, but just be aware, multiple choice questions, sometimes they throw in some weird simplifying. Not weird, just make you remember simplifying. But if you left the 2 in front, that's okay too. Yes? No? Maybe so? Not so bad, maybe? Okay. You don't necessarily have to write this next thing down. I just wanted to kind of give you the wording of it, and then we're going to do a problem. Oh, no, wait, just kidding. Let's do this one first. You do this. It is exactly what we were doing yesterday. Just some extra practice. There are a lot of rules.
My math grade on the SAT was like, I was really upset. On the ACT, it was really bad. Like, they gave you 60 math problems in 60 minutes.
Nice.
And that is not the speed at which I work. So yeah, there's like 5 problems towards the end. I was like, C looks good. Okay.
Is the ACT like the SAT where if you don't answer, you don't get penalized, or?
No, the ACT, if you don't answer, or if you put a wrong answer down, then it doesn't count against you. The SAT, they take away a point.
Right, right. So it's better to guess.
Yeah, I guess on the SAT too, though. The
I was very stressed when I took the SAT of knowing when to leave it blank. 'Cause I'm not gonna lie, on the English part with all those words, I really felt like I didn't know what any of them meant, and
That's what the English said about math.
right.
That makes you
Like the English part, I was just like, I seriously could leave all of these blank because I have no clue. Bread is to crumb as what is to what. That was always the example, and then you open the book and it's like words you've never heard of your whole life. And
Yeah, that was my biggest problem.
What is the meaning of this word? I'm like,
I don't know.
Maybe I should read a dictionary before this.
When it's a square root, I tend to write out my u because it helps me to simplify this before I go into the problem. So I'm gonna write my u prime like this. If you want to just do it as you go and simplify as you go, you can, but I just tend to write it out when it's something more complex like this. So u prime is going to be 1 over 2 square root of x plus 1 over the square root of x plus 1 times ln of 10. Is that true? Yeah, we could do a lot of things here. One thing we could do is you could make this over 1 and you could just flip that up, right? Make it a fraction times the reciprocal. You could multiply the top and the bottom by this denominator. You could just know this whole denominator is going to move to the bottom because it's a fraction in the top, right? I don't care which way you do it as long as we get rid of this fraction. So I haven't done this in a while, so I'm going to go the multiply by the reciprocal way. So if I multiply this up, it becomes 1 over the square root of x plus 1 ln of 10. Yeah, I don't know. It doesn't really matter what order we write this in. All over 1, right? Again, we could be fancy if we wanted to. Instead of writing 2 ln of 10, could we write ln of 100? We could. I'm okay leaving it like this. I just like to throw things out there and make you think a little bit.
So you wouldn't distribute the 2x plus.
You could distribute the 2 to the x plus 1. Also okay. Yeah. Notice up here when I took the derivative of this, I did take the derivative of the inside, but it was just 1, so that's why I didn't write anything. If that was something else besides x plus 1 in there, you might have to multiply the chain rule there. But again, that is what we did yesterday, but there are a few on your homework today just practicing that because, the best way I think to learn new rules is to actually apply them, and hopefully you don't just have the rules sitting right out in front of you and you're thinking about it, because that's what I do every time I do this, and I really have to think about what that derivative is. Okay, logarithmic differentiation. You could write this if you want, but you don't have to write all this explanation. Sometimes we don't have a rule for derivatives, like x to the x power. It does not fit the power rule. It does not fit a to the x rule because it's an x to an x, and that doesn't fit our rules. And so sometimes we can use what we know about logarithms to rewrite a problem and take the derivative. Not going to say it's always going to be the simplest process, but sometimes it's the only way that we have to do the derivative. And it says the process of introducing logarithms into a problem before differentiating is called logarithmic differentiation. When you take derivatives of logs, we don't call that logarithmic differentiation, but when we introduce logs into a problem in order to use the properties, that's when we call it that. Okay. So let's start with our nice x to the x, and then we'll do a crazy one. And then that's it. Oh, no, just kidding. Maybe I do crazy. Sometimes I like to. We cannot do the power rule because the power rule says this has to be a real number. X is a variable, and so you can't do the power rule. So then you might say, well, why don't we use the a to the x one that we did yesterday since it has an x up there? But that means a has to be a real number, not an x. And so this fits the category of not working with any of the rules I've given you. And I've given you all the derivative rules. I'm not hiding anymore. So you have to think about how could I rewrite this to get that x out of there? And could I ln both sides, and that would let me bring the x out front?
Or could you do
x ln of x over ln of L over L.
Let's try
I
this.
figured you could do ln of something over ln of something spelled as equal to 1 on the side.
But
That wouldn't work
yeah.
because there's nothing to
I'm allowed to ln both sides of an equation, and if I ln both sides of the equation, I can use that property of pulling the x out front. So I now have ln of y equals x ln of x. Does that look like something that I could take the derivative of? Yes, because I can do the product rule over here, yes? But I also don't have y anymore over here. I have ln of y, which means I'm actually going to be doing implicit, because I'm going to have to take the derivative of this with respect to x, and then solve for dy dx at the end. Make sense? So what would the derivative of ln of y be? 1 over y, but because it's y, we have to also multiply by dy over x. And what's really nice about log differentiation is you usually ln both sides, so it's always going to be that on that side, because it's just ln of y, the derivative is 1 over y, dy over dx, you just have to remember that. Over here, this one's kind of simple, but they can get a little crazy. But I am going to do the product rule, so remember, addition, you don't just take the derivative of one times the derivative of the other. So, the derivative of x is 1 times ln of x, plus, I'm going to leave the x alone, and what's the derivative of ln of x? 1 over x, so that works out really nice to just be 1, right? Stop me if you have a question. Good so far? So I'm going to rewrite this as, you might not need this step because you can just simplify as you go. It's our first one, so I'm going to actually rewrite it like this. 1 over y, dy over dx equals ln of x plus 1. But just like implicit that we did a few sections ago, I want dy dx by itself. So could I just multiply y on both sides? That would move that over. Like if I multiply this side by y and this side by y, I would end up with dy over dx equals ln of x plus 1 times y. What's different about this implicit is when we did implicit before, the x and the y's were all mixed up, and so our derivative had both x and y in it. But on these problems, it's always going to have y solved for. So you can always sub in what y equals in terms of x. So your last step is if y equals x over x, can I replace that with x, not x over x, x to the x? Every time, it's going to be solved for y. So your final answer shouldn't have any y's in it. Like you should be able to sub in because y is always going to be solved for. So I'm going to just say that's x of x times ln of x plus 1. If you want to put the x of x at the end, you can. You could distribute if you want, but you don't have to. We took the derivative of this. Our final answer is in terms of x. So that is our answer. So sometimes they're going to give you directions, use logarithmic differentiation, because there's no other way to do it. Sometimes they're going to give you just such a terrible problem that doing the power rule and quotient rule and product rule seems awful, and log differentiation is maybe a better way to go because you can separate things. So maybe let's look at it. Oh, here we go. This is my last one. Technically speaking, we could take the derivative of this as is. We could do the quotient rule. We could do the product rule as we take the derivative on the top, which would also entail doing the chain rule. But it's going to be a whole lot of steps, which I'm not going to lie, log differentiation, you might just decide that you'd rather do it this way. But this problem is kind of set up perfectly to do log differentiation because we can use the property of logarithms to separate this. Remember that multiplication of logs separates into addition, and division of logs separates into subtraction. So what I'm going to do is, just like the last one, I'm going to start by lning both sides. So sometimes you kind of make it look a little bit worse before it gets better. That should be our motto in calculus class. I'm going to do this in 2 steps just so you can kind of maybe follow it in your notes when you look back at this. But in the future, if you can do it all at once, do it all at once. But I know I can break multiplication into addition and division into addition of ln's. So I'm going to rewrite this as ln of x squared plus ln of 3x minus 2 to the 1/2, because multiplication goes to addition, and minus ln of x minus 1 squared, because division goes to subtraction.
So if we're dividing by both of them, we only have to subtract once.
Because if you put it back together, you would say multiplied and then divided by. And you might say this still looks pretty bad, but there's one more rule for logarithms. What can we do with exponents? We can bring them out front, which means we can even make these easier to take the derivative of. And usually I do this all in one step. But I'm going to write this as 2 ln of x plus 1/2 ln of 3x minus 2 minus 2 ln of x minus 1.
Subtraction, would that be like subtraction on top of division, or would that?
Like another subtraction down here.
Yeah.
You want to be careful. You either want to put parentheses and subtract the whole thing, or you do a minus and a minus. Like as long as you subtracted both, it would be the same thing. So if you had another x plus 1 here, you could just do minus x plus 1 and that would still work. Or you could just do 1 minus sign and put it in one parenthesis. So this might look terrible, like this is awful, but there's no quotient rule, there's no product rule. There's a little bit of the chain rule in the terms of u prime, because u prime is going to be 3 on this. But to me, there's less mistakes, because I can take these derivatives separately, and I don't have to worry about all those terms and simplifying. Like imagine simplifying the top of that quotient rule and trying to put it together. A little bit ugly to do. So now I'm going to take the derivative of this, and just like before, the derivative of ln of y is 1 over y dy over dx. And these all have constants in the front, but remember you can just kind of leave them there, however you want to show the work here, but like the 2, you can just leave it there, and the derivative of ln of x is 1 over x. And remember ln is u prime over u, so on this one if I take the derivative of the top, I would get 3 over the bottom, which is 3x minus 2. Minus 2, and the derivative of this one is just still 1 on the top, so it's just 1 over x minus 1. And again, you could have went ahead and put the numbers on the top with it if you wanted to. So I'm going to get 2 over x plus 3 over 2 times 3x minus 2 minus 2 over x minus 1. Do you agree with that statement? I used to make students get a common denominator here because I said it looks better to have a common denominator. But the back of the book on the one that you have in the book, they don't get a common denominator, and so people like revolted and said if it's not on the back of the book, I shouldn't have to do it. So I don't make you get a common denominator anymore. I think it looks better to get a common denominator, but you know, I have a common denominator on my paper because it works out that maybe you could cross something out, but whatever. But we're not done yet because we have to multiply this y over, and we're not just going to put y in there. And if you want to go ahead and plug in what y is here in terms of x, right? Y was this big ugly thing up here. When I got a common denominator, right, if you had a common denominator and it was all multiplication, then you could cancel some stuff out, and I actually got something to cancel out, like a 3x minus 2 canceled out, but it's still a pretty ugly answer, and like I said, the one in the back of the book, they didn't simplify like that, and so we just kind of stopped doing that over the years. because I don't want you to feel like it's fun. I'm just saying, I got a comment from one here, and then I have to do the other one, and they didn't even get a comment on me. So, you can just leave your answers super ugly like that. Exciting stuff, right? That's it for chapter 3. Like, this is what your test is, all this stuff. 3-9 day 2. This is also your last homework assignment that you'll turn in the test besides the review, which means if you're behind on homework, you might want to, check on that. Worksheet tomorrow, or tomorrow apparently. Review on Friday, test on Monday. So, we'll see. I could give you the review assignment tomorrow also if you want. If you want to be able to try to work on it and ask some questions on Friday. So, I'll try to get that printed out for you. So in case you want the worksheet and the review assignment, just to kind of get a head start on it. But otherwise, we'll have